Hi, everyone. Thank you for joining us for the next session of 3CQ events. Today we have Laura Ruetsche from the University of Michigan joining us. We'll be talking on scale invaders and effective field theory. Laura is you're a professor?
I'm a professor, yeah.
You're a professor at the University of Michigan, looking at philosophy of physics, particularly in quantum field theory, or infinite quantum theory, and also looks more broadly at various things. Currently is looking at renormalization and effective field theories, but also looks at feminist philosophy and related topics. But I'm very interested in learning more on scale invaders and what it has for today. So please take it away.
Thanks, Evan. Thanks for inviting me. I wasn't sure who the audience is, so this is going to be a field report, basically, on how some ideas that I think have been pretty familiar to physicists for a while now have been percolating recently through philosophy of science. And yeah, please bear with me if I just drastically mistargeted your background and interests. Oh, here we go. The philosophical setting is something called the scientific realism debate. So I'll begin with a quick introduction to that and then explain what ideas from physics are percolating, how the upshot of that percolation is a kind of new, sort of hypercharged by the best ideologies and technologies of recent physics, scientific realist view called effective realism. And I'm going to raise some questions about the viability of effective realism, questions I gather under the umbrella of scale invaders and instead of pessimism. So scientific realism, here's, I think, an irresistible question to ask, given a theory of physics that's succeeding enormously well, making surprising predictions, underwriting technologies that are mind-boggling, making surprising and accurate predictions over a wide range of phenomena. It seems like these theories of physics are trying to tell us things. What are they trying to tell us, and should we believe them? In particular, on the supposition that these theories are positing unobservable entities and processes, quarks, electrons, weak decay. Did the unobservable entities and processes these theories posit, are they really out there in a mind-independent world? That's the question of scientific realism. And the scientific realist answers this question, yes. We should believe what our best theories say, including what they say about unobservable entities and processes. And a kind of standard, and I think the most compelling argument in favor of realism is something come to be known as the miracles argument, I think because of this formulation due to Hilary Putnam. The argument goes, it's the only philosophy that doesn't make the success of science a miracle. The idea is these theories are working astonishingly well. That begs for an explanation. And the most attractive explanation, the irresistible explanation, is they're working as well as they do because they're getting things right. They're working as well as they do because the world really is the way the theories say they are. And something that's always struck me about how philosophy of science rolls is arguments like this, debates like this, are often conducted with respect to this generic placeholder theory T, posited to be extremely successful, but no more background information about it is given. And something that's striking about the miracles argument is, as compelling as it seems in the abstract, it really goes off the rails when you instantiate T. Pick your favorite successful physical theory. My favorite successful physical theory is quantum mechanics. If you run the miracles argument with respect to quantum mechanics, the first premise can't be better supported. It's the most successful theory we've ever come up with. The second premise is just baked in the miracles argument, so it seems like you're delivered painlessly to the conclusion. But the conclusion asks you to believe the world is the way quantum mechanics says it is. What way does quantum mechanics say the world is? We just can't figure it out. Most people think they don't know. There's sets of people who think they know. They disagree with each other. So this is a kind of interesting dialectic that I hope is going to play out in the rest of the talk between high-level philosophy of science, which considers physical theories, and all abstraction, and the way expectations and intuitions get morphed when those high-level arguments, those abstract arguments, are brought into contact with more detailed pictures of physics. So if you're not a realist, what might you be? You might be an empiricist. And I'll kind of give an exposition of empiricism by way of setting up a small dialogue between the empiricist and the realist. If you're an empiricist, you have the gall to think, no matter how successful a theory is, that's not a good reason to think that it's latching on to how the world really is. And it's not a good reason to think you should be exploring the theory with the view of trying to understand better what the world is really like. There could be other reasons to sort of explore and articulate and investigate a theory, but coming to know what unobservable parts of the world are really like without us in it is not one of them. And naturally, a realist confronted with one of these iconoclasts is going to say, well, empiricist, why does a successful theory work as well as it does? And I think a pretty good answer an empiricist could give, maybe the best answer an empiricist could give, is we've only probed parts of the physical world. We've got the experimental technologies and the conceptual insight to look into. And this successful theory T works as well as it does because it so happens that in those regimes, the regimes we've thought of to probe and are capable of probing, our successful theory T approximates the predictions of another theory, T-bang, T, where I'm introducing T-bang as a technical term of art for a theory that is the complete, accurate, full, total story of reality. So T works as well as it does, not because it's getting things right, but because it's mimicking theories that get things right, where we apply it, T. And to give some flesh to this proposal, consider the law of universal gravitation, which is extremely successful, extremely impressive. It's conciliant. It predicts things nobody expected. It unifies a wide range of phenomena. It's a tremendous, tremendous theory. It's a kind of what the world without us in it is really like. Deep structure, things we can observe, posits, central gravitational force that acts instantaneously at a distance across Euclidean 3 space. And from the vantage of general relativity, which I'm using as a stand-in for this final theory, T-bang, none of those exist. Central forces, gravitational forces, instantaneous action at a distance, Euclidean 3 space, none of them are there. That's to say, the law of universal gravitation, notwithstanding its tremendous success, gets things dead wrong. Nevertheless, the way it gets things dead wrong affords us excellent devices for coordinating expectations about low velocity, medium distance phenomena. And this commentary about what's going on with the success of Newtonian gravitation, it's as if it were true. And I want to underscore the force of the as if is not that it's pretty close to true, but not quite true, like it would be if there was a 1 over r plus epsilon squared force, or gravitational phenomena throughout in a 3 plus 1 dimensional spacetime, where the 3-dimensional spacetime isn't quite Euclidean. It's not that it's approximately true, close to true. It's not true, but insofar as we use it to gauge phenomena we interact with, it's as if it were true. And this sort of suspicion that this is going on all the time with successful theories propels empiricism to the view that we should believe what T says about the phenomena we've explored, but we should withhold belief from what T's picture of what lies beneath, of hidden springs, unobservable entities and processes. And yeah, like I gave what I thought was the most compelling argument for realism. Now I'm going to sketch what I think is the most compelling argument for empiricism. It's something that's come to be known as the pessimistic meta-induction. And it just consists in the historical observation that the history of science is littered with theories. I just gave you an example of one, Newtonian gravitation, that were well loved in their heyday, but subsequently rejected as false. And the pessimistic meta-induction is the future is going to resemble the past. So why believe our favorite theories now are going to enjoy a happier fate? Presented with this argument that we shouldn't believe even our best theories right now, a kind of standard realist response has evolved known as divide et impera, which is to distinguish your favorite theories' idle theoretical wheels, the things doing the load-bearing work in the empirical success of the theory, from the things doing the load-bearing work in the empirical success of the theory, and invest belief only in the latter, only in the parts of our present theories that are the reasons they're succeeding, and as the reasons they're succeeding are expected to persist in their successors, And the thought is that we can sort the wheat from the chaff in our best physics and repose belief only in the wheat and the stuff that's doing the explanatory work and getting things right. We're going to be proof against the march of forward progress, because forward progress is going to preserve what's right about our present theories. It seems like a good idea in general, but the empiricist is dubious that we can right now effectively and successfully perform this sort. We can, without the benefit of hindsight, tell what about our current theories is enabling them to succeed so well. So that's sort of where the dialogue about scientific realism languished for like 20 years until earlier in this century, when philosophers of physics sort of bold enough to engage actual interacting quantum theories, not tame linear ones, but actual interacting ones, saw resources there for making progress on the realists' project of responding to the pessimistic meta-induction by identifying the belief-worthy aspects of current physics right now using a tolerably precise and reliable selection mechanism. And the position that leverages insights from current physics to advance the cause of realism against the pessimistic meta-induction has come to be known as effective realism. So I'm going to give a big picture sketch of it and then develop some details, always operating very schematically and loosely. So the thought is there's a fruitful alliance to be had between scientific realism and effective field theory technologies for identifying, given a domain, the right variables for doing physics in that domain. And then the thought is this is the connection to the divided emperor response to the pessimistic meta-induction. The right variables are what the realist needs. They're guides we can identify now to the realist-worthy content of an effective field theory, the part of an effective field theory that's going to be carried over into successful physics. And just call this big idea effective realism. And my dialectical trajectory in this talk is to suggest that to identify the right variables, these effective field theory technologies need to appeal to scale separation. And there's a reason to be a little nervous about appeals to scale separation if you're a scientific realist, but that reason is a reason to celebrate if you're a physicist. And my cute name for the cause for concern about reliance on scale separation, assumptions about scale separation, is scale invaders. But on the way there, I want to motivate and explicate effective realism. And again, the big underlying idea is it's a divide and conquer response to the pessimistic meta-induction that emerges from a solution to a felt puzzle about our best current physics. And the felt puzzle, I'm going to call it the renormalizability puzzle overview. Quantum field theory, so they use Lagrangians to calculate empirical quantities, but there's a hitch. Naively pursued, these calculations yield meaningless infinities instead of finite predictions we can test in particle accelerator experiments. There's a conventional fix to this, perturbative renormalization. It's to calculate in a much more sophisticated way, but observation, provocative one, is that not every Lagrangian submits to sophistication. Not every Lagrangian is renormalizable. But there's good news. The Lagrangians in the physics we care about and develop and test in our accelerators, the Lagrangians of the standard model, are renormalizable. But the good news prompts another puzzle, the renormalizability puzzle. And it's the puzzle, if most Lagrangians ab initio a priori aren't renormalizable, why should we be so lucky that we live in a physical universe governed by renormalizable Lagrangians, exactly that rare kind of Lagrangian that we can tame using existing techniques of perturbative renormalization. So as Porter Williams puts it, and this is a philosopher of physics, but he's echoing what lots of physicists also say, it just seems incredibly lucky that we could describe so much in particle physics using renormalizable QFTs. Why are we so lucky is the renormalizability puzzle. And as a prelude to how effective field theory technologies address the puzzle really quick, because you already know what I'm talking about, review of Lagrangians and their perturbative renormalization, and mostly just to fix notation in a conceptual frame for thinking of Lagrangians as living in a space of Lagrangians. But think of a Lagrangian as a function of space-time fields and their space-time derivatives. Throughout, I'm going to use the massively simplified example of a Lagrangian that depends on a single field, a scalar field, assumed to be symmetric under reversing its orientation, so that the monomials of fields and their space-time derivatives appearing in it are going to be even powers. So kind of generically, think of every possible Lagrangian that fits this profile. It's going to be a sum of functions of fields and their derivatives, powers of them, where each function is multiplied by some sort of coefficient I'm going to call a coupling. In real physics, you're always going to get a term that depends on the gradient squared, the kinetic term. You're often going to get a mass term that depends on a coefficient m squared. And the remaining terms, the terms third order or higher in fields and their derivatives, I'm just going to call interaction terms. In this huge space of Lagrangians, there's some that are very tractable. For instance, the free field Lagrangian, taken as a classical theory, is exactly soluble from its space of classical solutions. We know how to follow a process of canonical quantization to build a Hilbert space and define acting on that Hilbert space operators representing field variables and their conjugate momenta that constitutes a quantization of the theory, and thereby achieve a full-fledged quantum theory in the form philosophers love and explicitly realized Hilbert space entity. The problem with free field Lagrangians is the quantum field theories they give rise to are deathly boring. If we want something to happen, we've got to add interactions to the free field Lagrangian. And think of a Lagrangian with all possible interactions added to it, all possible monomials of the fields consistent with symmetries. As residing in a space, I'm going to call it G of Lagrangians. I'm also going to call it coupling space, where the address of a particular Lagrangian of the space is just afforded by the coupling coefficients that specify the relative size of each term. Now we're working in an interesting space of Lagrangians where there's interactions, where there's things happening, but there's this technical problem that even the very simplest interacting QFT Lagrangian, the phi-4 Lagrangian in 4 space-time dimensions, in some sense eludes our mathematical reach. We can't explicitly characterize the classical solution space, so we can't follow this route I just charted from the classical solution space to a fully realized quantum theory. We don't have to canonically quantize it. But that doesn't need to stop us. We can still involve this Lagrangian in characteristically quantum calculations and wrest empirical predictions from it that are distinctly quantum mechanical, and thereby use it for a basis of a working quantum theory, even if it's not fully realized explicitly mathematically. And the way we do that is by perturbation theory, where the idea is to approximate empirical quantities of interest as a perturbative expansion in orders of the coupling coefficient around a precise value predicted by the free theory, where the succeeding order of correction are nth order perturbative corrections, and perturbation theory tells us how to calculate them. And then we hope if we do the perturbative expansion and truncate after a few orders, we get an empirically sensible number that we can compare to experiment. And again, operating extremely schematically. In the context of interacting quantum field theory, one way to calculate the perturbative corrections or the amplitudes they're underwriting is path integral techniques, where very big picture, what you're doing when you're doing a path integral calculation of an amplitude is integrating some function the Lagrangian is informing against a range of field configurations at a measure that you pretend exists over the range of field configurations. And here we get into a sticky point, which is a field configuration's energy and momentum depends on its frequency. And the expression I've got there has us calculating empirical quantities by integrating field configurations of all energies, including arbitrarily high ones. And this would be just fine if we were working with a boring free Lagrangian. But if we're working with an interacting Lagrangian, we'll resort to perturbative approximations of the path integral. Feynman diagrams help us ride herd on the perturbative approximations we need to do. And what we find out if we're working with an interacting Lagrangian and approximating an empirical quantity perturbatively and integrating over every possible field configuration, every possible energy, we find that the perturbative corrections individually at second order and higher become infinite. And that means we're trying to calculate an empirical quantity, but instead of getting a nice finite number to compare to the deliverances of experiment, we get infinite numbers. We basically rendered our theory empirically meaningless. This is the problem of ultraviolet divergences. There's other kinds of divergences that the set interacting quantum field Lagrangian calculations, but I'm going to focus on ultraviolet divergences. And here's where the techniques of perturbative renormalization come to the fore. It's catastrophic that when you calculate perturbative corrections, you get infinities. These divergences are catastrophic. But the techniques of perturbative renormalization are techniques for order by order doctoring Lagrangian's coupling so that at each order, you get a finite perturbative correction. You feel like if you can pull that off, obviously there's questions about whether when you add up all the terms, you get a finite number, but still you feel like if you can pull that much off, you've succeeded. But success was experienced especially by the framers of these techniques, as kind of predicated on some suspicious, dodgy, hand-wavy, opportunistic approximations. Notwithstanding how dodgy it seemed, the perturbative calculations guided by the techniques of renormalization proved to be stunningly, shockingly accurate to 1 part in a trillion. So this introduces a very special class of very mystifying Lagrangians that surrender finite predictions, indeed horrifically accurate finite predictions when subject to techniques of perturbative renormalization. Let's call these Lagrangians renormalizable. And again, they're a special subset of Lagrangians. How special? Well, Dyson articulated a criterion for identifying which Lagrangians are renormalizable that hinged on the mass dimension of the terms, the interaction terms appearing in it. I don't need to explain what mass dimension is. And according to Dyson's criterion, a Lagrangian is renormalizable only if it contains no interactions of mass dimension greater than 4. And I'm going to call an interaction renormalizable if it has mass dimension of 4 or less. So that circumscribes the special set of Lagrangians that, when subject to techniques of perturbative renormalization, surrender sensibly finite predictions. This brings us back to the renormalizability puzzle. Our space of Lagrangians, a typical member of the space, has interaction terms arbitrarily high in mass dimension. So elements of the space of possible Lagrangians that are obedient to the symmetries we've posited that are renormalizable are a very, very teeny subset of all possible Lagrangians. It's a 3-dimensional subspace of this infinite space of possible Lagrangians. The subspace spanned by the kinetic mass term and an interaction term of the form 5-4. So whereas the space of possible Lagrangians is infinite dimensional, the space of renormalizable Lagrangians is 3-dimensional. And that's the renormalizability puzzle, given that physically interesting, successful Lagrangians seem like they're renormalizable. Why should nature be described by a renormalizable theory when the space of possible options is so much larger than the space of renormalizable Lagrangians? Okay, so here's a resolution of the renormalizability puzzle that inspires the position effective realism. And the resolution is predicated on what I'll call an autonomy of scales hope. Now, described, so I've just acknowledged our technologies are limited, our particle accelerators achieve very finite energies. We can't use them to probe physics at energies higher than the energies they can achieve. And introduce the idea of an effective energy scale. I'm calling it lambda, and think of it as setting an upper bound on the energies at which we can actually test our quantum field theory, as circumscribing a range of phenomena. Our quantum field theory is beholden to describe accurately. The autonomy of scales hope is this. It's something like lambda circumscribes a cohesive autonomous domain for physics that, put another way, in order to generate predictions empirically adequate up to scale lambda, we need only survey field configurations of up to energy lambda. And that the higher energy stuff, the stuff that lies beneath, isn't going to make a difference to the phenomena we're probing with our particle accelerators. Now, if you're animated by this hope, you're going to posit a Lagrangian that describes phenomena within the scales we care about, within the effective scales. when it's integrated against field configurations, a domain of field configurations that's cut off at the, I'm going to call this the ultraviolet cutoff lambda. And this pair, this Lagrangian and this energy scale that circumscribes the domain, you're doing path intervals to generate empirical predictions with constitutes a theory. It's making a bunch of predictions, a scale lambda effective theory. It's a scale lambda effective theory because its domain, both of definition and of application, is limited. And you're hoping that it works just fine in that domain. So compare the expression defining using a scale lambda effective theory to define an amplitude with the totally unrestricted theory we started out with, the theory where you generate predictions by integrating against all field amplitudes whatsoever. It turns out that's in some sense a scale lambda effective theory where the scale itself is infinity. But preliminary moral is if they're being applied in this way, if they're being integrated against truncated spaces of field configurations, quantum field theory Lagrangians don't describe phenomena on their own, but only in conjunction with the range of energies over which they're integrated. And although the two schemes above, the one where the domain of integration is truncated, the one where it's unlimited, they feature the same Lagrangian. They're different theories because they integrate against different energy scales to get different answers about what's going on. They make different empirical predictions. And this is enough to define a kind of interesting kinship relationship on the space G of possible Lagrangians. And the definition proceeds as follows. So pick a very high energy cutoff, lambda UV, and consider a theory defined by a Lagrangian L in conjunction with that cutoff. And let this Lagrangian be any Lagrangian whatsoever in the space, even horrible, non-renormalizable Lagrangians. And I'll pick a lower energy scale lambda, an effective scale, maybe a scale we can actually probe in our particle accelerators, and embrace the autonomy of scales to hope that there's a scale lambda, low energy scale, effective theory that reproduces the original theory's low energy predictions in the sense that we do all perturbative calculations truncated appropriately, the predictions you make about phenomena manifested at energies less than lambda using the lambda L prime and lambda reproduce the higher energy theory's low energy predictions. I mean, if your hope is fulfilled, if there's a way to fulfill the autonomy of scales hope and identify for any lower energy cutoff an effective Lagrangian that mimics the low energy deliverances of the higher energy theory, then you define a transformation on the space of Lagrangians. The transformation tells you, given a high energy theory and the energy it's defined at, and a lower energy, what lower energy Lagrangian mimics the predictions of the high energy theory with respect to phenomena accessible at the lower energy scales. And this transformation you defined is a Wilsonian renormalization group transformation on the space of Lagrangians that live in G. And yeah, again, note, even though it maps Lagrangians, this renormalization group transformation, what it's establishing an association between is theories that are defined not by Lagrangians on their lonesome, but in conjunction with cutoff scales. Same idea with fewer equations. In the space of Lagrangians, or Lagrangians is coded by its coupling vector, the coefficients of its kinetic mass and interaction terms. And the central dogma of this picture of renormalization group transformations establishing flows through the space of Lagrangians is that changing the cutoff scale that you're using to do integrations and get empirical predictions out of a Lagrangian and demanding that the physics be the same, there's only one V in the original, since the cutoff scale is arbitrary, means the couplings in the theory must depend on the cutoff scale. And so these RG transformations of the equations, kind of consolidating them, describe what's come to be known poetically as the running of the couplings, how the coefficients in a Lagrangian have to vary as a function of cutoff scale in order for the physical content at a scale you're interested in to be the same. Okay, so that's the idea of running couplings under renormalization group. How do they run? There's a famous venerable analysis due to Polchinski, where the plot is you fix an ultra-high energy cutoff scale, you pick a Lagrangian. This is a space of weakly coupled scalar field theories, so don't pick any old Lagrangian, pick one that's close to the free Lagrangian, pick it, and start the RG flow. And what Polchinski establishes, the standard of precision appropriate to this sort of question, is that for cutoff scales significantly lower than the original UV cutoff scale, the effective Lagrangian that consorts with those cutoff scales to reproduce the empirical predictions in the low energy domain of the original Lagrangian, no matter what the original Lagrangian was, within reason, it's going to be well approximated by a Lagrangian featuring just 3 terms. Any other term in the original Lagrangian gets squelched, multiplied by factors of the ratio of the lower energy scale, the high energy scale, by the iterated RG transformations. And the thing that struck Polchinski as miraculous is the terms that are squelched, the terms that if they started out in the high energy Lagrangian as you visit renormalization group transformations under the Lagrangian to get a Lagrangian that works at lower energies, the bad terms, the non-renormalizable terms, they get suppressed. They get multiplied by many, many, many powers of the ratio of the low energy cutoff and the ultraviolet cutoff. And what that means is effective Lagrangians, the Lagrangians you integrate against your domain of field configurations truncated at effective scales in order to get predictions at effective scales. Low energy Lagrangians, for all intents and purposes, except for trivial corrections, they reside in this tiny corner of theory space consisting of renormalizable Lagrangians. And that's earth-shattering. That's a super profound explanation of why so many real-world Lagrangians are renormalizable. The explanation is something like real-world Lagrangians are Lagrangians we used to do effective physics with, and the Lagrangians that convey the content of effective physics are going to be, for reasons of the suppression of non-renormalizable interactions in this autonomy of scales, hope-informed renormalization group picture, are going to be renormalizable. So in light of the above RG analysis, this is Williams again, but again, he's echoing what a lot of physicists say. It no longer seems like incredible luck that so many useful quantum field theory Lagrangians are renormalizable. That's the RG explanation. It's documenting that physicists say the same thing. Okay, that's the background. It seems like the idea of effective physics and the pursuit of the idea using renormalization group techniques has, with respect to puzzles proper to physics, some powerful payoffs. The insight a number of people had in the last decade or so is there's payoffs for philosophy as well. And these payoffs are something like as follows. Recall the challenge for scientific realism was to identify, given our best current physics, the parts of them that won't be undermined by the future march of progress, to respond to the pessimistic meta-induction by pointing to our best theories of physics and saying, these parts that I can identify right now here, these parts are going to survive into future theories. The idea of effective realism is, I just told you how to do that. How you do that is you consider theories in the ambit of renormalization group techniques, and you appeal to those techniques to identify the terms, the interactions that span the space of a low energy surface of attraction for the renormalization group flow. What Polchinski tells you is no matter where within reason in the space of ultra high energy Lagrangians you start with, when it comes to the low energy Lagrangian that mimics its deliverances for the phenomena we care about, there's going to be just 3 terms in it. So, come what may, no matter what the high energy truth is, and no matter how much of it we reflect in our theories of effective domains, only 3 terms are going to matter. Those are the right variables. Those are the 3 terms that are going to survive. We find out more about the high energy truth, or as we incorporate more about the high energy truth into our picture of the physics we're probing with our accelerators. So the thought behind effective realism is renormalization group methods can be used to identify structural features of an effective field theory that are stable or robust across a broad range of candidate models for describing nature at low energies. And that inferences about the structure of nature at these low energies won't be undone when our current effective theories are eventually embedded in stories that describe nature at higher energies. And this is a really cool idea. This is an idea that is responsive to what's happening in physics. It's, instead of talking about a generic theory T, it engages the gears of specific physical theories, and the machinery is used to make sense of them and wrest predictions from them. But it's also admirably judo-like, like underdetermination and agnosticism are been the tools, the weapons of anti-realists, of empiricists, but the effective realist turns those tools against them and by saying, yeah, okay, there's things we don't know, but we can tell you this. It doesn't matter that we don't know these things. We know the following. These three terms are going to be in an effective Lagrangian no matter what. So I try to get you pumped up about effective realism and how resourcefully it takes tools from modern physics and uses them to reinforce and make more plausible and articulate and precify a position in the scientific realism debate. Why don't I like it? And I'll go a little bit quickly because we're running out of time. So the story, according to the story so far, effective field theory technologies appeal to scale separation, the difference between the high energy cutoff and Earth energies we can probe, to identify the right variables for an effective field theory's domain of application, and that lays the groundwork for effective realism about that theory. And here's where I think there's something to worry about. It's that our favorite effective theories aren't ones where we've got a handle on their more fundamental forebears. We don't know what the high energy truth is we're integrating out to get our favorite effective theory. Let's say they're unpedigreed. And I think these things I call scale invaders pose a threat to this strategy for being realists about an unpedigreed effective field theory. And to warm you up for feeling the threat, I'm going to evoke David Wallace, a very persuasive and charismatic philosopher of physics. Here he is thinking about different pairs of an effective theory and its higher energy forebear. One pair he just stipulates is classical mechanics. That's the effective theory, big things. And its higher energy forebear, what lies beneath, is non-relativistic quantum mechanics. And this is the pair where we know both the effective theory and its forebear. And the pair where there's an effective theory and an unknown forebear, the pair where there's an unpedigreed effective theory, is quantum field theory and my T-bang, some as yet unknown deeper theory, which gives a mathematically self-contained description of the short distance physics. This is all Wallace. And Wallace observes, and this is the warm-up for the concern I'm going to try to motivate, there's some important differences between these pairs of effective theories and their higher energy forebears. Most obviously, we know the underlying theory in the first case, whereas we only have the sketchiest idea of what lies beneath our best quantum field theories. And Wallace comments, this makes it difficult to delineate the domains in which quantum field theory is approximately isomorphic to the underlying theory, since we have to describe those domains in QFT language rather than underlying theory language. Second different point, when using classical mechanics, when we're not sure whether it's valid or not, we can cross-check with the underlying theory because we have the underlying theory. In the case of QFT, we haven't got the underlying theory, so we don't have any independent check on whether our guesses based on QFT about the world are right. The only test available for its validity are empirical tests guided by calculations we can conduct. So here's the very idea of scale invaders. I'm going to quickly give a couple examples of scale invaders and close with my point that scale invaders seem like a problem for effective realists, but an opportunity for physics. So the idea of scale invaders is without the underlying theory in hand, we can't be sure either that the domain of our favorite effective field theories are ones whose boundaries the underlying theory respects, or use the underlying theory to check that our effective theory describes phenomena within those domains accurately. And that means we can't appeal to the underlying theory to argue that our effective theory is safe from scale invaders. Or what I mean by a scale invader, I'll give examples, but this is the idea. It's something that makes empirical trouble for an effective theory in its avowed domain, not some weird thing way off stage at high energy, bizarre, something in the avowed domain of effective field theory that it wasn't ready for. Alerting us we've been too quick to assume that domain to be a protectorate, to be under control. And why is this salient to the scientific realism debate I've been talking about? It's that the technologies effective realists appeal to, the technologies that enable us to identify the right variables and respond to the pessimistic meta-induction. They make assumptions about how to delineate domains and carve out empirical content. And I think this leaves right variable realism, effective realism, about unpedigreed effective field theories. And that's the kind we've got, vulnerable to scale invaders. Here's a warm-up fable making concrete what scale invaders are. So imagine a 17th century sect, I'll call them hiatonists. They, for reasons clear to them, but beyond reach of history, they track stars and the cluster Hyades to see whether the apparent relative distances between those stars change over time. Their equipment's homely and workaday. They got telescopes, they got sketch pads, they got an elaborate filing system, but they're very, very dedicated. They observe and record inter-Hydean stellar distances night, and also day when there is a suitable eclipse. And during the daytime observations, what they learn is that the stars appear in positions systematically different from the positions they appear in at night. And moreover, the closer to the sun's periphery a star appears, the more its apparent position shifts during an eclipse. And this is something utterly beyond the capacity of their favorite theory of gravity, Newton's theory of gravity, to predict. This comes out of a total surprise and disconfirmation of Newtonian gravity. And so the thought is, with respect to Newtonian gravity, this cult's eclipse observations are scale invaders. But nobody cares. Yet when Eddington observed the same phenomena 150 years later, he and Einstein got all the attention. I'm describing what Eddington saw on the solar eclipse expedition. And so some morals. One thing is these eclipse data, they make trouble for Newton's theory of gravitation. But Hyatonists didn't need to explore exotic high-energy regimes using super fancy equipment to find trouble for the law of universal gravitation. They just needed to look carefully at the night and day sky. The trouble they found underscores that the successful track record of effective field theories that so impresses us is indexed not only to the domain where we're applying an effective theory, but also to the sorts of phenomena it's occurred to us to look for, to collect. And it just could turn out that the range of salient in-scope phenomena confronting an effective field theory could be much wider than we imagine. And it could harbor scale invaders like the eclipse data the Hyatonists collected that nobody cared about. And all this seems to me like a material for a kind of pessimistic meta-induction about effective field theories. Okay, that's one scale invader. You're going to miss the ascent of pessimism part of the talk, I'm sorry. Here's another example of scale invaders, torn from, well, last century's headlines. So in the 30s, like a few minutes after radioactive decay was discovered, Fermi proffered the four Fermi theory, the beta decay. And in this theory, the neutrino appears as a mass zero neutral fermion that interacts directly with three other fermions. So the figure on the left is beta decay according to the four Fermi theory. Later on, theories of the weak force, they refine this picture. They populate the world with additional fields and particles, and their model, beta decays, mediated by a massive gauge boson, the W minus. Also later, Jianzheng Wu conducts experiments suggesting that weak interactions violate parity conservation, and that way to take that on board is to take neutrinos to be all left-handed. So according to the story thus far, each successive picture of neutrinos is a pretty good guide to the successor. It's not that there aren't neutrinos, it's just that there's also omega W minus particles. It's not that there are neutrinos, it's just they're all left-handed. But the story keeps going. In the 60s, solar neutrino detectors, including this one in the Homestake mine, which are essentially giant vats of liquid underground, sometimes just water, other times like cleaning fluid. They register responses that don't align with theoretical predictions based on models of what's happening in the sun. And these data are an unresolved problem for the standard model, the solar neutrino problem. And as with the Hyatonists, the people running the Homestake experiment, they didn't need to explore exotic regimes using particle accelerators the size of the solar system to discover these data recalcitrant to embraced by the standard model. They just needed a mindful of cleaning fluid and some argon for their detectors. So with respect to the standard model, I'm suggesting solar neutrinos are scale invaders. They're something doing things we didn't expect that we didn't foresee. So this is going to be the denouement. It's thought that the solar neutrino problem can be addressed through a mechanism called neutrino flavor oscillation that requires neutrinos to be massive. So project, how do neutrinos get to be massive? There's a lot of options. On some options, they're Dirac fermions, and they get their mass through a Higgsy mechanism, but there's puzzles about if this is what's going on, why have we seen some things we should see. Another option is maybe they're not garden variety Dirac fermions, maybe they're Majorana fermions, a kind of fermion because its own antiparticle can be left-handed and massive. If that's the case, there's a process we should be able to see that we should be looking for in accelerators called neutrinos double beta decay. Maybe neutrinos get mass through an entirely new mechanism. Maybe this is the one empiricists are really rooting for. We'll eventually settle on a way to respond to the solar neutrino data conveyed by a theory so unlike past and present neutrino theories that neutrinos don't appear in it at all. But the point of this is work is afoot. It may be one of the most exciting reaches of particle physics right now on what's going on with neutrinos. So all these options of development, except for the last one, where our minds are blown, they extend the standard model, but they differ with respect to their novel posits. They posit different fields, different interactions, different mechanisms, different symmetries, different interpretations of existing symmetries. They predict different phenomena. And they're all vibrant, fecund areas of physics development, some of which could lead physics in the right direction. And I think if you polled a bunch of working physicists in the right mood about how they feel about the scale invaders constituted by solar neutrinos, you'd get a response that whereas for effective realists and their progenitors, scientific realists, scale invaders are a problem because they call into question whether we really have a handle on the empirical regularities and the theoretical structure that delivers them, a handle that gives us a response to the pessimistic meta-induction. Scale invaders, I'm hoping I suggested make trouble for that idea. Scale invaders are troublesome for scientific realists. But they represent opportunities for physicists. They're exciting for physicists. They're how physics, which after all isn't done, that's the whole point of this and reason we're embarking on this sort of question about scientific realism. Physics isn't done, so what attitude should we have towards physics under development? And an attitude I can imagine physicists having about physics under development is that scale invaders are good for it because they indicate the joints and junctures and places in your current theory where there's work to be done, work that can take theory in novel, unforeseen, exciting directions. So my closing thought is, it's a question, it's not a thought. my closing question is it awkward for scientific realists and or philosophers like me who care about the scientific realism debate that when it comes to scale invaders and our best current theories of physics, there's a sense in which effective realists are rooting for our best current physics to keep working exactly as projected, keep saving the same phenomena. But working physicists are rooting for scale invaders for opportunities for theory development. Okay, that's it. Thank you.
Excellent. Thank you, Laura. Do we have any questions from people watching? I'll ask the first question. Oh, we have one from
Well, I have some. I was waiting to see if others wanted to go first. If you want to go ahead, Evan, that's fine.
I'll save my question for last because that's usually what I do.
Okay, so should I go ahead?
Yes, please do.
Yeah, here. Okay, so yeah, thank you, Laura. It was an interesting talk. I'm not quite sure I entirely understand your objections to EFT. But that being said, I've never been a fan either. Primarily because I feel, I mean, maybe this is what you were saying. Sometimes I try to read the slides and you jump ahead. But anyway, the reason why is I feel there's just too much arbitrariness, or almost too much. So if you've got something that isn't working, the way I understand this is throw in non-renormalizable terms and multiply by the lambda scale to get the dimensions right, and then adjust things to get agreement. Well, sure, but I mean, what good is that? And I guess I know people that love it, but this is the main reason I never get excited about it. Am I missing something here? Do you agree with this objection?
I'll say I do agree with this this concern. I mean, it's kind of a concern that once the space of interactions you're allowed to use is as capacious as it is for EFTs, you can back engineer an EFT to accommodate just about any phenomena. But the real question
to me, that's the biggest problem with it.
Yeah. And I think I'm maybe channeling the same problem from a different direction. So I'm going to insert as an aside, Francisco is all over this. It's the kind of plaything of a single scalar field setting for effective theories just takes off the table a lot of interesting effective theory techniques, including a way of pursuing scale separation by comparing masses of heavy and light particles. We need more than one field, a heavy field and a light field, to do that. I think some of the technologies you're talking about are technologies for pursuing effective field theory using power accounting parameter that's a ratio of a heavy field and a light field mass that sort of allows you to organize terms, including non-renormalizable terms. You should have been worried when I went through the amazing explanation of how renormalization group approaches address the renormalizability problem. You should have been worried that that explanation doesn't leave any room for effective field theories that use non-renormalizable terms, but there's plenty of effective theories, including the four Fermi, chiral Lagrangian. But anyway, to sort of fuse your kind of concern and my kind of concern is, okay, there's a successful track record. We can marshal the resources we have and the flexibility we have and the skills we have to use theories like this to explain phenomena so far. But it seems like before I should commit wholesale to this is the right way of thinking about the world, I should have reason to believe future phenomena, including phenomena different from the ones I'm tossing in enough non-renormalizable terms to accommodate, to explain. So I've definitely got that worry. And I've even got a more paranoid worry that maybe the whole framework, just like the whole framework of central forces acting at a distance across Euclidean space of modeling things by Lagrangians that are functions of fields, in fact, isn't going to be adequate to physics. So I don't think we're disagreeing. I think effective theories are really cool. I'm a big fan of them. I just don't think you should believe everything they tell you to believe.
Well, I certainly don't do that, but I guess, I mean, Fermi's theory is the other way around. It was something that started as an effective theory because it worked, but everybody knew it couldn't be right. And when we went to high enough energies, we saw that it's fixed, by the simplest possible Higgs mechanism there is, which has made all beyond standard model believers unhappy because the LHC has seen nothing but the Higgs. And it means supersymmetry is in trouble, which means string theory is in trouble. And anyway, regarding your last comment or question, it'd be interesting to do a survey with people, but I'm very much of the latter viewpoint, that a lot of the progress in science is finding out what does not work.
Yeah.
And you should be satisfied that you've advanced something instead of finding the correct ultimate theory. And I think perhaps sadly, maybe those younger here can comment, but I feel within the particular subdiscipline of high energy physics anyway, it's been overemphasized that the object of the game is to find the next Einstein and find the next theory. I just don't think this has been helpful. In my career lifetime, we've learned what does not work much more than what does, with quantum gravity. And I mean, the standard model, it works great. Could be here for 1,000 years, assuming we're here for 1,000 years.
Right.
Yeah. Anyway, that I just feel that you didn't commit yourself. My sense is you're probably in the latter category.
Yeah.
Okay.
No, thanks. And my experience when I give this talk, people say, scale invaders are great. Why are you acting like they're bad? And they're not bad for me. I think they're bad for effective realists.
Yeah, probably, yeah. Okay, yeah. Anyway, thank you.
Thank you, Rob. Do we have another question, Chris?
Yeah. So you've given kind of a version of this talk a few times, and I imagine you have talked to some of the realists out there, EFT realist folks. I'm curious, I have my own kind of interactions with them, but I'm curious what you have gotten in response to this, because I've been trying to kind of latch on and understand what their response to this kind of argument is, and I think I'm struggling.
Yeah. I don't think they've spoken sort of officially ex cathedra at length about what their response is. Maybe I should say, ask them and tell me what they say. But I should also say, I've got this cognitive deficit that I don't really understand what a scale-dependent ontology is, and this makes a lot of sense to them. I mean, I'm obviously trying to say even the scale-dependent ontology seems like it should be in trouble if there's scale invaders. I think, maybe the view is I'm crying wolf. Like, come on. The standard model is going to be around for 1,000 years. You're not going to, you can take my neutrinos from me when you pry them from my cold, dead hands.
Mm-hmm.
Nobody ever claimed to erect a scientific realist position that was such as to demand credence won from all rational inquirers. And maybe if there's a kind of consistent response, it's that skeptical worries you're evincing. Of course, skeptics are going to worry about anything. We're not that worried about.
Yeah, interesting. Sorry, I didn't mean to cut you off.
I still think we're onto something. Yeah.
Yeah, I think the interesting thing about this version of the talk is you've now given some concrete examples of scale invaders that seem to fall outside of the kind of framework that we had been operating in prior. Yeah. And that seems to put more meat on the bones than the paper version you had, 3-4 years ago on universal gravitation.
Mm-hmm. Yeah. And actually, when I gave the talk with the examples, the main response was the one I just described to Robert. Like, you're acting like scale invaders are a problem, but we think they're cool. And which is just I think they're cool too, and I'm glad you think they're cool. But I feel like thinking they're cool and being an effective realist on the model I laid out is a position with some internal dissonance.
Yeah. If it's supposed to be doing anything for you, then you should be worried about this sort of stuff, I think. Yeah. Thank you, Laura.
Thanks, Chris.
Excellent. Do we have any other questions? Okay, I'll quickly ask one. Oh, wait. Did you want to ask something?
I could ask later, but it was mostly if you had other examples in mind. I'm just trying to like put my finger on what other kinds of things could space invaders be, like any other, like, I don't think this is a term that you would use, but maybe other conceived alternatives or unforeseen phenomena.
Yeah, I mean, there's people who think they have ways to test for signatures of Planck scale physics in a kind of achievable, close to tabletop experiment. Like they think they can get it running in the next few years. They have funding, and that would be scale invaders. That would be a manifestation of Planck scale physics at accessible in the early 21st century domains. I mean, it's a feature of them that they're hard. Imagining them a priori amounts to basically contriving the theory of physics, or at least its basic outlines that predict something unexpected. So it's hard to come up with armchair examples. If you have an armchair example from the future, you shouldn't be doing philosophy. You should be, being a famous physicist. But yeah, my prediction is the future of science will let us know what, with respect to our best current science, besides neutrinos, are scale invaders. That's my prediction.
Thanks, Laura.
Thanks.
Excellent. I also have another question myself. So I've always been very strongly on the scientific realist side, but only quite recently I've shifted, I think, quite a bit to the more anti-realist position and taken much more seriously this pessimistic induction argument. And I really like this idea of scale invaders that you're bringing up, but I do want to maybe just raise a bit of an objection just to challenge things a little bit. So all the examples given have kind of been these arguments in hindsight, or the examples in hindsight, and I'm just sort of wondering, as you sort of raise the question, with these examples, how would we identify scale invaders today? Because we wouldn't be able to readily recognize them, or if we do try and recognize them, they'll be disputed. And I have two cases in mind, but I'd like to hear your answer maybe to this.
Yeah, and this is sort of continuous with Francisco's question. I think it's awfully hard to, from the armchair, identify future scale invaders. Like in the first example, part of how the example worked is I made up the Haydnists. There weren't people in the 17th century looking at that star cluster to see whether stars moved. What gave anybody the idea to do that was there was another theory of gravity, Einstein's theory, that said light bends around the sun. That motivates, seeing what happening with the stars behind a sun during an eclipse. And the kind of generic point is what, with respect to current physics, has the status of a scale invader. It's hard to identify prospectively, only with the hindsight of successor physics that identifies the domains in the regime of intended application of our best current physics, where its predictions aren't borne out, that we can recognize the scale invaders. So I can't give you an algorithm for identifying scale invaders, but I don't think I should be able to. It's the very reason we're epistemically vulnerable, the very reason I claim we're overreaching when we trust that just because our best physical theories have worked in the domains where we apply them so far, they're going to keep working in the domains. The very reason we shouldn't trust that is we can't anticipate which aspects of those domains that we're not looking at, because we haven't got the theoretical underpinning to think to look to them, are going to harbor the difficulties. But you said you had two examples or thoughts, or
Yeah. So before I actually give the examples, I just wanted to quickly follow up, because I do feel that there is maybe some not algorithm but argument in where to look, because based on the examples given, it seems we should not necessarily be looking at higher energies or in these extreme cases, but we should just be looking on the everyday, more low energy cases, where we might not expect to find disagreements, but which there would be signatures and upscale invaders. And that would tie into the examples given. So the two things I have in mind, one of which is a negative example, and which is maybe a bit more, I would say, the positive example, at least it's open. So the negative example would be the muon's anomalous magnetic moment, which was seemingly discrepant, or was discrepant with Samuel predictions, and that disagreement grew. But eventually, the theoretical predictions changed and became in agreement with the current experimental status. So there's hopes, I guess, for new physics or the scale invader there, but it went away.
Yeah.
And that maybe is a bit more of a high energy physics example, but there's also the low energy physics discrepancies that people aren't as aware of. And so the one I have in mind is the neutrino, but not the neutrino, the neutron lifetime problem, which is where neutrons approximately live for around 800 seconds, I believe, or on that order. And there are experimental tests to try and measure that. And there are two different experimental schemes that come up with different predictions, or different results, I should say, which are around 1% discrepant, like on the order of 10 seconds. And there doesn't seem to be any explanation given, and from what I can tell, that's statistically significant. And there's maybe a better argument to be given that this could be a scaling, because this is a discrepancy between two different experimental schemes. Although, again, this is disputed, of course, because all these things are disputed, and whether it could be explainable by other factors that haven't been taken into account. And so, again, it's always difficult. But these low energy discrepancies, I feel, are where we should be focusing our effort more so than the high energy potential discrepancies. And so, from that perspective, it seems to be giving some argument on where we should be looking.
Oh, great! I love those examples, and I mean, a virtue of the recommendation focus your energy on low energy phenomena is that you can actually do that. We don't know what the high energy phenomena really are, and yeah, of course, anytime there's recalcitrant data and theories under development, there's going to be a bunch of different kind of reactions, including refining, tuning the theory to accommodate the data. And yeah, who's to say who's going to win in the end? I'm saying I'm betting and hoping the weirdo future physics we haven't thought about is where we're going to wind up driven to by some of the right low energy phenomena once we twig it. So I'm afraid when I agreed to do this, I was confused about the time, and I have to leave soon for an eye doctor appointment. Is that okay?
That's fine.
Yep.
I think we're done here as well. So
okay. Thank you very much.
Thank you, Laura. Thank you very much.